So, good morning, physics students. I have a bit of a problem this week. We're doing the same thing we did last week, Q is equal to MC delta T, and showing how there's transfer between one object to another object. And I wanted to, give you a demonstration, something to think about, something to, make this engaging and fun. But I can't think of anything. So I was going through the internet and I thought, maybe we'll just go through the internet together. So I'm going to see how this works. Going to try to, enter into how mind works as far as, figuring out how to present online. So here we go. We're going to go over to the internet. Thermal equilibrium demonstrations. We're in screen 1. All right, so what I want is something that is engaging, something that is like real life and fun. Classroom resources, dramatic demonstration in thermal conductivity. All right, standards, topics. Okay, here we go, dramatic. 38 seconds, even better. We've got, I don't know what that is, wire. Looks like copper wire in the thermometer. So we got, can't read what that is. All right, we got some heat there. Something dramatic is going to happen. Take out the copper wire. It's going to be hot, but not really hot because it's metal. That's it. I mean, don't touch that. Okay, that's not what I would call a dramatic demonstration. All right, here we have, that's just an animation. We don't want that. Here we go. Maybe this is something. 2 minutes, we'll speed through it. Try to get through the commercials and things. Let's see.
Thermal equilibrium.
2 beakers with hot water and
hot
cold
water in a large beaker and some cold water in a small beaker.
Well, this is...
And some cold water in a small...
You heat up some water. And then there's some cold water. And then we're going to pour the cold... You just set the cold water in the warm water. That's... I mean, yeah, they're going to reach the same temperature. That's not cool. Zeroth law is way too simple. Here we go. Heat transfer projects for kids. This is something that we can do at home. Science fair experiment. They're a little young, but, we can adapt it. Make it a little more rigorous. Where's the video? I don't want to read. Where's the video? Science fair worthy projects. Is there a video? Fun heat transfer projects. Fun heat transfer. A wow-worthy project making Play-Doh change colors as you play. Simply heat from the heat of your hands. Magic Play-Doh recipe. Ooh, color-changing Play-Doh. That's what we want. Is that going to let me go there? Heat-sensitive, color-changing Play-Doh. Come on, please work. I know my internet's slow. I'm sure this is like everyone's problem. Is it not going to go there? Oh. And we all wait. How to learn how to make color-changing Play-Doh. Heat-sensitive. It's going to tell me we need some special ingredient, isn't it? Here we go. Of course, we have to wait for the ad. Does anyone else feel like this is their life now? You're just like looking for something fun to do and you have to wait for an ad. And then maybe it's not even there. Doesn't even tell me how long the ad is, so I can skip through it. So how y'all doing today? It's Spirit Day. I mean, while I'm taping this is. Maybe I can ponder catapults while I wait. Is this going to do a thing? Here we go. 1 minute. We can handle that. I like the music though. Okay, he may have just had dirty hands. His hands look pretty clean. Inside was a different color. No, it is changing colors. So there is a little heat transfer going on there. I don't know if it should be getting warmer, so it's changing colors when it's warmer, right? I want to know how to make it. I don't want to just watch him play with it. Where's the how to make it? Where's the recipe? He's just going to play with it the whole time? That was not worth waiting for. Ah. All right. Let's see if we can get something that really explains what heat. I have to actually go to page 2. That's odd. Usually there's like a cool demonstration right at the beginning. What do we have? Thermal equilibrium properties, a guy swimming. Is there any that's chemical equilibrium. Nothing? Equilibrium lab. Thermal, well, maybe, at least it's real life. Maybe this is something. Copyright, we'll just ignore it.
Hello everyone. Ice cubes are much colder than this normal water. When we put the ice cube in this water, the water doesn't freeze. The water becomes cold and the ice cube melts. Exactly, this is what has happened here. When a solid receives enough heat, it melts. The ice is melting, which means it is receiving heat.
Riveting.
And water is losing heat. Hence, it is becoming colder. Now, the water due to melted ice is still much colder than the other part of water in the glass. So, it receives heat from the other parts of the water.
All right. So, I can't find anything. I'll look up that Play-Doh recipe. We'll see what's going on. It might work. It might not work.
All right. So here we go. I found the recipe finally for the amazing Play-Doh demonstration showing thermal exchange from your hands. And of course, when you get to the demonstration, it calls for a special powder that you can only get on Amazon, some kind of color changing temperature powder. Of course, if you use that, it's going to, so that's, we're not going to do that one. Instead, I found a demonstration that I think you will appreciate much, much more. I'm pretty sure you're really going to appreciate this one. So what this involves is if you have an aluminum cup, let's say, perchance it happens to contain in there 225 grams of water. So the mass of my water is 225 grams. It's in an aluminum cup. We don't know the mass of the cup, but we know the mass of the water. And we are also going to use a copper stir. So we got this stir that we can continually use if we need to. We know the mass of the copper stir. The mass of the copper is going to be 40 grams. And we do know that the temperature of those is just standard temperature. They're in the room. They are at 27 degrees Celsius. However, to this system, where's my hand? To this system, we are going to add some silver. So I have some silver over here. Oh, wait, nope, can't be touching it. That's hot silver. This silver is a temperature 87 degrees. So we're going to very carefully, carefully pick up our silver. And you can see the steam just boil off as steam, and it's stirring, and the heat is leaving the silver and it's going into our system. But we know the mass of the silver is going to be 400 grams. And we know it was warm to start with. The initial temperature of that was actually 87 degrees Celsius. And what's going to happen here is the heat is going to leave the silver and go into the water. But because the copper stirs in the water also, it's also going to be absorbing some heat. So the heat leaves the silver and goes into the water and the copper stir. But since we're using an aluminum cup, the heat is actually leaving the silver and going into the water and the copper stir and the aluminum cup. And we're going to ignore the fact that there's also air and the heat is going to be coming off of it because that makes the math hard. So we're just going to no air. And those are the three things. So we've got water and copper and some unknown mass of aluminum that is going to be taking in the heat. And we know the silver is the thing giving off the heat. And what's going to happen is it's not going to stay at 87, but it's also not going to stay at 27. We do know the final temperature of this thing is going to be 32 degrees Celsius. So that's an important thing. If we know what the equilibrium temperature is, we know that this amount of heat left and went into these things. So we should be able to figure that out because Q is equal to M times C times delta T. We do need to know the C values for each of these things. Okay? So you grab your reference table and you take your C values for those things. So we have, here's your C value for copper. Here's your C value for silver. Here's your C value for water. So those are those things that we needed. And you put them in your list. I'll let you do that on your own. And you can say, well, if we have the silver is giving off the heat, so how much heat does it give off? It's going to be the mass. I'm going to change that so that it's in kilograms, times the specific heat of silver, which was 234. Make sure you add the units to everything when you're putting in your list. And times the change in temperature. We know it changes from 87 to 32. We know it changes from 87 to 32. So I'm just going to write 87 minus 32 here. And we're going to solve that to figure out what the amount of heat is that's coming off of the silver. Now, heat isn't a vector quantity, but I'm going to write negative just so I remember that it's the heat that's coming off. Up here, this amount of heat is going to go into these things, but we've got three different things. We've got Q is equal to MC delta T when we're talking about the aluminum. We've got Q is equal to MC delta T when we're talking about the water. We've got Q is equal to MC delta T when we're talking about the copper. Now, we can fill in everything for the water. 4186, and what is the temperature change there? It goes from 32 to 27, so that's 5. And we can solve that. And then over here, we've got Q is equal to the mass of the copper, which was 40, times the specific heat of copper. Is it 387? Times that change in temperature. So there's going to be some heat here. So the idea is to solve this. This amount of heat goes into these three things. We don't know the mass here. We do know the specific heat of aluminum to be 900, I believe. And we do know its change in temperature is also going to be 5. So what I'd like you to do is solve this. This amount of heat is given off. You should be able to solve those two amounts of heat. Based on that, you can figure out this amount of heat, and then you should be able to figure out the mass. In order to get credit for this class, I'd like you to solve for M in this amazing demonstration. I'll see you on Tuesday at 3:30 with an answer to this question and to work on the other homework questions.